In this video, we'll be taking a look at some of the key concepts for utility network management for ArcGIS. The utility network is now Esri's long-term solution for network management for the next 15 plus years. Geometric network and support for that technology is drawing to a close, and now's the time for organisations to think about what a modern GIS solution for utilities means for them. In this presentation, we'll look at topics covering the aspects of the information model for data and network management. This video is a continuation of the ArcGIS webinar series, An Introduction to Utility Network Management for ArcGIS. To access this webinar recording, follow the URL on screen or email us here at utilities@eagle.co.nz. My name is Aaron Sapsford and I'm GIS Utilities Practice Lead at Eagle Technology based in Wellington. Let's start by talking about some terminology. In a utility network, operational networks are expressed as domains. So your domain is the commodity that your utility carries. To understand some of the key data concepts, we'll first take a look at asset packages. An asset package is a particular flavor of file geodatabase which is designed for each of your industry's domain network requirements. The asset package is where you will define your features, subtypes, domains, and other operational and business attribution that you might have. It's also a collection of other metatables contained in an asset package that define how your network will behave. Business rules for connectivity, attachment, containment, and schematic diagram templates you can use to build out your own schematics. Esri Provided Utility Network Foundation Solution Templates with pre-canned asset packages for each industry domain that can be configured to suit your own needs. They're intended to be changed, and this is by design. These templates don't limit you to the model that's provided. Because the asset package is a file geodatabase, it's essentially portable and disposable. And this is where you'll take your first look at the data model and ultimately stage your GIS data before deploying it to your enterprise. Also has pre-populated sample data for Naperville. So if you want to take a look at a sample network and see how it behaves, you can. Check out solutions.esri.com. The utility network information model is structured in such a way so that there are a smaller number of feature classes that represent your network assets. So these are your master spatial tables that locate and describe your network assets. There are 3 feature classes which represent a structural network as points, lines, and polygons which support your domain network, which is made up of 5 feature classes which represent your operational network, which we'll talk about shortly. Included are tables which hold information about terminal configurations for devices. There are business rules which describe how each of your features in the network interact with each other. Tables to store information about how your schematic diagrams are stored, shared, and laid out. And your topology, which puts it all together to keep your network valid and connected. It's worth noting that support for non-spatial features will be coming to the utility network soon. Non-spatial features are a way of representing things like ports, splice points, buffer tubes, and individual fiber connectivity inside a telecom network. The service territory is a polygon feature that's needed to create your utility network. It's Z and M enabled to support your network in the 3rd dimension. It defines the maintenance extent of your network topology and can be viewed as a bounding polygon when your topology is enabled. Service territory can be multi-part and also can be edited in case your network territory may change or grow over time. The structure network defines what carries or supports your domain network. These are designed to be leveraged right across your network and can be shared by multiple networks. There are 3 feature classes for all structures. Structure junctions are points that can either be a structural feature to which a device is attached or a container of multiple devices. Structure lines are linear features that carry a resource. Structure lines can contain other structure lines that can contain operational lines. Structure boundaries are the polygons that contain other structures, devices, lines, and assemblies. So all of these support associations or structural attachment or containment. Your domain or operational network is determined by the type of data model being used. So this manages the operational part of the network that carries your commodity, whether it's power, water, or gas. There are 5 feature classes or layers created for each domain network. Devices are point features. These are compact features through which your utility resource flows, and devices can affect the state of your flow of your resource in several ways. Devices can optionally have terminals, where there are multiple distinct entry or exit points on each device. Junctions are also points, and they're locations where lines connect to lines, or lines connect to devices. These are connected but passive as distinct from devices, which change the operational flow of your network. Junctions are placed as needed mid-span or at the end of lines to complete the connection of all the features of a utility network. Lines, as the name suggests, are linear features that deliver your commodity. So these are your pipes or conductors. Lines can be connected to other lines via junctions or devices, and can also be contained in assemblies as well as containers. Assemblies are point features that represent a collection of other devices and junctions. Assemblies designed to show a single point on the map, but can be modelled so that any other features and their connections can be visible. Subnetwork lines define the current extent of a resource, so this differs slightly from normal lines as they aren't directly edited like other features in the domain network. For water or gas utilities, subnetworks would be generated for pressure or isolation zones, or for electric utilities, these would be designated as either circuits or feeders. And because of switching devices, subnetworks can and do frequently change. So these need to be generated on demand or post-processed after all your edit workflows have been completed. Subnetwork lines are used for tracing and can be configured to roll up totals like combined load or pressure, customer count, and the number of switchable or protective devices on your subnetwork. Asset groups are categories or generalized descriptions of your structural or network features. Or another way of thinking about an asset group is describing what your assets are. Asset types further define or categorize asset groups into specific functional descriptions of your network features, or describing each subset of your assets, describing what they do. With the utility network, you can model devices to a much higher degree of realism using terminals. The utility network allows you to optionally model these ports with terminals on device features. Not all devices require the definition of terminals. With the utility network, you can model devices to a much higher degree of realism using terminals. The utility network allows you to optionally model these terminals on device features. Not all devices require the definition of terminals, but if a device has 2 terminals that are equal and interchangeable, such as the 2 sides of a switch or a valve, then you don't necessarily have to define them. Some of the situations where you would need to define terminals would be if your device serves as a subnetwork controller or a source, devices with 3 or more physical ports or connection points that you need to model, devices with 2 ports that are distinctly different, such as a high side and low side port on a transformer, or devices with connection points that will only allow flow in one direction, such as a check valve in a water system or network protectors in the electric system. Terminals don't appear on the map. They are logical connection locations that control how other features connect through valid paths. Tiers are a way to logically represent your network in segments. Tiers can be managed separately or grouped together, but they are able to interact with each other. Tiers are named and can also be grouped. Partition networks could be operationally separate, but logically connected. For instance, an electric utility might want to have their high voltage or distribution network partitioned from the low voltage network, but still be able to propagate traces upstream or downstream through both tiers. Hierarchical tiers would generally be used for mesh networks like a water or gas distribution network, where each are defined by certain properties such as different districts, pressure, or isolation areas. For domain networks with partition tier definition, both radial and mesh topologies are supported. Partition tiers are sequential in nature, like an electric network, and are independent from each other. Features within a tier will only participate in one subnetwork within that tier. Traces can be propagated across tiers as long as you define the target, and traces will be covered in an upcoming video. Hierarchical tiers only support the mesh topology, like water and gas. This allows you to model networks that can be nested, so that each tier within a domain network are dependent on and inclusive of all subsequent tiers. So features inside a tier will participate within each higher tier and subnetwork. We've mentioned subnetworks a few times now, so to explain this a little further, we see subnetworks as a smaller subpart of your network inside a tier. So the example I often use is an individual electric feeder or a specific isolation zone in, say, a water network. The subnetwork is defined by the subnetwork name, and this is unique and defined at the subnetwork controller for your source. So this would be a single device for a radial network, or one or more for a mesh network. The table holds a single record for each subnetwork in your utility. Subnetwork line we talked about a few slides ago is created by a trace task on a valid network topology with no errors. The update subnetworks task then stores the roll-up of your network property on an aggregated line feature, which you're able to represent to your users in their maps so they're able to run traces. This would generally happen after all of your edits are posted and validated as a manual task, or you can script it to run as a maintenance task by an admin. Subnetwork system diagrams can be optionally created when the subnetwork lines are updated. And there's a system managed field in your domain features which you can specify whether a feature participates in the subnetwork based on its connectivity or lifecycle status. Network diagrams are a symbolic representation of geographic information drawn using visualization techniques using pre-canned diagram algorithms. Also known as schematics, these diagrams are a way of showing a simplified representation of your network to explain the network structure and the way it operates. These can be created by your users as a quick way to show logical views of sections of the network or the result of a network trace. Diagrams can be stored and edited and saved inside the network and made available and secured for viewers of complex or critical operational portions of your network like a substation. There are a number of different tools available in ArcGIS Pro to create and maintain your diagram layouts. You can edit white space and layouts to suit your particular situation. Network rules. An edge junction rule is the most simple. The rule type defines which point feature, asset group, and asset type can snap to which linear feature, asset group, asset type combination. This is more or less the same way you would enforce a geometric network rule using coincidence. A junction-to-junction connectivity association is used to connect points to each other by using implicit connectivity. Junction-to-junction connectivity rules manage this type of association. This rule type also supports connection to terminals on device features. So you can define connectivity associations for device and junction feature classes in a domain network as long as the network rules exist to support the association. The edge junction edge rule type further defines how network elements can traverse intermediary devices or junctions. An example of this would be a main pipe connecting to a service pipe by a particular type of fitting. Containment associations enable the modeling of assemblies or complex devices in your network while controlling map clutter. Containment allows for dense collection of features to be represented by a single feature on the map, where devices, junctions, and lines can be placed inside of objects such as substations, switch cabinets, trenches, and ducts. This improves visibility on the map and promotes better representation of your assets in maps. A polygon container defines a general area containing many features, like an electric substation or water pump house. Linear container can span some length, like a trench or a duct bank, that would also contain multiple lines. Utility network supports nested containment as well. So a nested containment, a container feature can contain another container feature, which in turn can contain your network content. Like a substation can contain a junction box, and then the junction box can contain electrical devices. Similar to structures and structural attachment associations, resource can't flow through containers. Traces can be configured to include the contents of containers or traverse across them. You can define structural attachments from devices, junctions, and assemblies in a domain network to structures in the structure junction feature class. You can also define structural attachment from one structure junction feature to another. Point features can be directly attached to other point features, for example, a transformer attached to a pole, or line features must have an intermediate attachment point attached to either the endpoint or the midspan vertex. You can define what features in your structure network support structural attachment associations by assigning the structure association role. Another example of a structural attachment is a stormwater manhole access point in line to a pipe. This is useful when you trace your network, but only if you want to return structures that are associated with the network, even though the resource doesn't traverse them. So when assigning association roles, deletion semantics are configured to control the user experience when working with structural attachments. This controls the behavior of features when a structure is deleted. So for example, you can specify which attachments need to be removed or detached before you can delete the structure. Information inside of the network topology is stored in a graph persisted as binary pages. This just allows things like tracing and diagram functions to read and process information about the network in a more efficient manner, as opposed to retrieving the information directly from individual features in your network, as you would in a geometric network trace. Connectivity is defined by feature restrictions at the class level, then by network rules defined by the valid asset group and asset type combinations. Network topology is enabled to enable normal network tasks like tracing, editing, validation, and error checking. When your topology is disabled, you're then able to perform administrative tasks like adding rules or assigning association roles to assets. It's also recommended that if you're loading large amounts of data, it helps to reduce the overall processing time if you do this activity while your topology is disabled. Dirty areas are polygons, which can be displayed as a sublayer in your utility network group layer in ArcGIS Pro. They represent a part of your network that's changed but not yet been validated against the topology. Any changes to geometry, attributes that define network properties or associations all create dirty areas. These can be accessed in ArcGIS Pro after the network topology has been validated or enabled. Error features may appear for any network features that could cause you issues. This is another way of ensuring your feature edits comply with your topology, making sure your data is much better going in. Rules supporting connectivity based on geometric coincidence are checked when the network topology is either validated or enabled. So after the topology has been validated or enabled, error features for any network feature that's going to cause you issues are system generated. Rules controlling associations are also checked when you try and create or import a new association when your network topology is either validated or enabled, but the error generated will be on the feature to indicate the association that's not valid. A list of all the topology errors and potential solutions are available in the ArcGIS Pro help. Well, that concludes this video session. There is a lot more information that we could have covered, but I hope this gives you a good overview of some of the key concepts. For more information or questions you have about the content covered in this presentation, please contact us here at Eagle at the email address on screen, utilities@eagle.co.nz. Also, we're presenting more utility network content. Migration planning. Looking at what you'll need to start considering when planning to migrate to the utility network, and the utility network in action. So the team will take you through some more in-depth demonstrations and workflows with real-world data in a utility network, covering editing, connectivity, tracing, schematic diagrams, and more. Thanks, and have a great day.